In this podcast, we have a very famous person. His name is Jon Williams, and he is from Viridi. And let me have Jon tell me if I pronounced anything wrong, and Jon can also introduce himself.
You actually got it right on. And Viridi is a Latin word, and you might be one of the only people I've spoken to who pronounced it properly, so thank you.
That's because I was watching the Netflix Roman series last night.
That'll do it. Yeah, that'll do it.
Do you know which emperor came up with that term?
I don't, but I mean, essentially, Viridi just means green in Latin. If you've ever had a verde sauce, it's a derivative of Viridi, right? It's a green sauce.
Oh, green. Okay, great. So let's learn more about your green self and a little bit about your green company that you're the CEO and founder of.
Yeah, this started about 10 years ago, and it really started what I would call more of a curiosity and a hobby than it did a business. And when I looked around, not just the country, but the world and battery development, it seemed like everything we were doing as private industries, government, and research facilities was focused on electric vehicles. And EVs obviously are vehicles in general are a significant portion of our carbon footprint. And obviously they consume more fossil than probably any other market segment. But as a piece of our total GDP, passenger vehicles are about 3%. So if we look at our GDP as being $1, passenger vehicles make up about 3 cents of that total dollar of GDP.
That's an interesting metric because a lot of times I hear people talking about percentage of CO2 and all that kind of stuff. So basing it off of GDP, that's great.
And I guess I'm thinking a macro way. And as I looked at it, I said, okay, if we're really going to transition off of fossil and it's going to be a meaningful long-term shift to a different energy platform, we have to address the other 97%, right? We can't just electrify passenger vehicles. And the reason we weren't doing it at that time, and really the reason we haven't done it since, after I spoke to a lot of experts and brought a few of those into the company, it really came back to safety, Sean. We allow vehicles, passenger vehicles and other on-road vehicles to have catastrophic failures. And a catastrophic failure is where the vehicle or the car really burns somewhat out of control until it consumes its own energy and it stops. Now, the reason for that is that most of our roads don't have fire hydrants and other fire protection in a meaningful distribution way because we accept those type of failures on road. But that's the only place in our entire economy that happens, right? We don't allow devices inside of a building to go into a catastrophic failure and burn the building down. We don't allow the release of smoke to basically inundate structures so that people can't get out or be safe. So if we're going to take this incredibly dense, reliable energy storage platforms that we've invented and put them in the other 97% of our economy, they have to be fail-safe. Meaning if everything goes wrong with the chemistry, if everything goes wrong with the protection systems, they can't cause a secondary event. And I didn't know at the time we could do that, right? But it was a business premise that I felt pretty strongly about. And we went on a path to try and develop that. And as we did it, really what we found out was the best chemistry in the market today. So the one that has the most energy density, is the most flexible from a temperature standpoint, has the greatest number of cycles, loses the least amount of capacity over the life of the chemistry, is lithium ion NMC derivative chemistries.
Okay, let's just tell people what NMC is. That's lithium, nickel, manganese, cobalt oxide.
Yes.
And as opposed to a lot of people are talking about LFP, and that's another type of lithium ion that's lithium iron phosphate, and it doesn't quite as much energy per weight, which is specific energy. Oftentimes people mistakenly call it energy density when it's talking about energy per weight. And then my car, it's an older Tesla, if they have such thing now, but it's over 8 years old, the warranty expired. And that one is NCA, which is similar to the NMC. Mine is NCA, lithium, nickel, cobalt, aluminum oxide.
Yes.
And
so
so
basically the nickel cobalt chemistries.
Yeah, the cobalt. Yep.
And they're finding a replacement for cobalt now. And I think that'll happen. But essentially the lithium nickel chemistries,
yep,
you're seeing this in your 8-year-old Tesla, right? They have great cycle life. They have great longevity. It's just a very flexible, adaptable storage technology. And the key to it is, Sean, in my view, is it's the only technology that we've proven we can scale. And scale in this industry is gigawatt hours, hundreds of gigawatt hours, not hundreds of megawatt hours. Because we're talking about displacing 60% of our energy that we rely on today. So we go through this whole research project and we come up with really two significant reasons for battery failures, catastrophic failures. One is external issues, right? So if two cars get into an accident and you cause physical damage to the pack system, there's a probability that you'll force that pack system into a catastrophic failure. Not every time, but it could happen. Moisture, water getting inside the pack, right? Other what I would call outside influences that enter the system can cause the chemistry to fail. We spent 3 or 4 years solving for that. And the way we solved for it was we built small pack systems that we put in compact construction equipment, and we put the equipment into the field. And the way contractors are contractors, they pretty much did everything they weren't supposed to do with battery systems. They cleaned them off of fire hoses and they ended up under mudslides and they fell off trucks on the highway, and everything that happens in a construction environment, which is never compliant with the use profile, happened to this equipment. And it allowed us to really harden and engineer all of those outside influences not to have an impact on cell failure. Once we did that, we were really left with the chemical issue of thermal runaway.
Yeah, and so thermal runaway, maybe we can talk a little bit about what that is too. So it's kind of like a fire, right? One battery catches fire and then it catches the next one on fire, or it gets hot enough where it makes the other one hot enough.
That's exactly what you're doing. So really what happens is inside the cell, and I'm going to reach the limit of my technical expertise here. As energy passes back and forth, right, through the cell, you're pushing these particles in and out as they charge and discharge, and they pass through the cathode, which is separating the negative and the positive side of the cell.
Yeah, so let's even define that too. So the cathode is the part that we're talking about when we're talking about NMC, NCA, and LFP. That's the cathode. And then the anode is going to pretty much be carbon, and sometimes it has some silicon in it.
Exactly. And again, as a cell charges and discharges, there's physical stress on the cell because as you charge it, it expands a little bit. And as you discharge it, depending on the speed that you discharge it, it can heat up. And as those cycles happen over the life of the cell, you can get to the point where the cell builds up so much resistance that it starts to generate too much heat in that charge discharge cycle. And where you started with this, if you get too much heat inside that cell, if you get that cell temperature up to 160, 170 Celsius, it sets off the material in the cell, right? It causes thermal runaway, which is really just an instantaneous release of the cell's energy. And that release gets up to 600, 700 Celsius, right? It's a spectacular release of energy.
Yep. And another thing too, though, is that sometimes people don't understand is they think that there is going to be some perfectly safe technology. And anytime you're storing energy, it can get released all at once, even if it's a flywheel spinning. If it breaks, it can explode. A car in the garage, especially with a gas tank, full gas tank could be a big release of energy. We're going to always have some sort of release of energy potential there, but it sounds like you're working on figuring out how to make it safer.
Yeah, so Sean, that's probably the most important piece from an education standpoint for this transition from fossil to electric, primary electric energy sources. If it's energy, it means that it has potential to release. Now, we engineer that energy to release in a specific way, but there's always the potential that energy is going to be released in a non-specific way. And to your point, if you're using pulleys and you have a heavy weight that's up in the air, the rope or the cable that's holding that weight can break and the weight will fall to the ground, right? That's a
yeah,
most rudimentary.
That's a release of energy. Yep.
It's release of energy. Now, where you started talking about energy density as opposed to energy by weight, that's
specific energy. Yep.
Specific energy. That's the really unique part of this chemistry. Is the good news is there's a lot of specific energy in that cell technology. The bad news is there's a lot of specific energy in that cell technology.
Great. Yep. Exactly.
So when it goes wrong, there's a very significant release of energy. So we accepted the fact that at some point a cell is going to fail, and there's a probability, not likely but remote, that when the cell fails, it can cascade into the energy around it. Our typical packs have about 4,320 cells. A 100 kilowatt hour pack on a Tesla has about 7,000 cells. If one cell lets go, it's an event, but it's not uncontrollable. But if 5,000 cells let go, there's no stopping it, right? It has to consume its own energy before you're going to have it go out. So what we looked at was, okay, if we know a cell's going to let go and it's an event that we could measure, can we stop it at the cell and prevent propagation from occurring? And it's probably worth talking a little bit about propagation, right?
Yeah, it
Propagation,
doesn't sound good.
well, it's just a chain reaction, right?
Uh-huh.
So
Yep.
what happens is that one cell goes off and it acts like a fuse that lights off the energy. We knew we couldn't solve it with chemistry, and we knew that we had eliminated all the external influences that could cause failure. So the only thing that was left was architecture, right? Can we engineer inside of the pack a passive system that if a cell lets go anywhere in the pack, we can hold on to that release of energy and prevent it from transferring to the next cell. And
Yep.
that's what we did show. As complicated and as simple as it gets,
Yeah.
the architecture inside of our pack is passive. There's no mechanical or electronic systems that control it. It's material science, right? So it's different materials organized in a specific way. And when that cell lets go, and it lets go at 600 to 800 Celsius, the great thing about it is it only lets go for about 1.5 seconds. So if you can hold that energy for about 2 seconds, you prevent the spread of that energy to the next cell. And that's the way we test, right? We wire up all the cells around the trigger cell, is what we call it. So when we put it into failure, we watch the temperature on that trigger cell get up to 600 to 800 Celsius. And then we watch all the cells around it never get above 100 C.
What kind of makes me think of a controlled explosion is the cylinders in an internal combustion engine, right? So we have those preventing those super hot flames from gasoline or diesel from exploding.
Think about this, right? Go back 150 years, right? When Rudolf Diesel invented the diesel engine, it probably took 30 to 40 years to figure out how to make that engine safe.
Uh-huh. He started with biodiesel, didn't he? With that.
I think that's all that existed, right? There
Yeah.
wasn't, he was burning probably cooking oil at the time.
Yeah.
But again, right? I mean, a diesel engine is a series of rapid explosions, same as a gasoline engine, right? We're lighting fuel inside of a controlled cylinder to force a reaction. That's the road we went down. And look, we spent millions of dollars destroying packs to the point where we were doing a destructive test of a 20 to 30 kilowatt hour pack every week. And I think the unique thing about Viridi is we probably have accumulated more real knowledge of destructive testing, I think, than any other entity that I know of. And as we've talked to the Department of Energy and others down at the Oak Ridge Labs, they've confirmed that. We just have a tremendous base of knowledge at this point of how these cells fail and what they look like when you push them into an extreme condition. And the way we did that, Jon, was we basically wrap the cell with a heating element and we take it from ambient all the way up to 170 Celsius by coming up at 5 Celsius.
Pretty hot. So 100 is boiling. So that's really hot.
170 is pretty hot, but
it's like glowing.
But you have to get the cell to fail past the internal fuse, the internal vents, right? All the safety. So you have to push past those safeties if you're going to get a catastrophic. And because we have to test repeatedly for CSA and DNV testing, we had to show them that we could replicate a failure in a repeatable way. And that was really, it took us a year to get to a methodology where we could show failure at the same point every time. So look at it, outside of the fact that it's our lab techs love watching stuff go, it was infuriating because it took us about 3.5 years. And I will tell you, I lost my patience on more than one occasion.
And so the lab techs are just doing destructive testing and blowing things up. Sounds like a fun job. Yeah.
I kept telling them, guys, your job is so this doesn't blow up. Stop.
Oh, so it doesn't blow up. I was thinking maybe you're sitting out in front of a prison waiting for the pyromaniacs to be released, but I guess not.
Like, the whole point of this is it can't go bang. So anyways, we got through that. And once we got through it, we took a single 50 kilowatt hour pack to CSA and DNV to do third-party validation of a destructive test. And
maybe we can even clarify this too, like a pack is a bunch of cells.
Yeah, so a pack is 4,320 cells. In our configuration, it's 270 modules. We take 16 cells and build them into a module, and then we put the module in series and parallel inside the pack. They get a specific output and voltage.
Great. So cells, modules, and then packs.
Yep. And look, we forced 2 separate cells inside of that 50 kilowatt hour pack simultaneously in a catastrophic failure.
So 2 cells having failure at the same time, is that sort of like as rare as winning the lottery? It sounds, if I
It
was
would be,
driving my car, having 2 cells fail at the exact same time after going for 10 years without having a cell fail.
yeah, so that would be like riding a unicorn, winning the lottery,
Uh,
and something else at the same
yeah,
time.
I do have a unicorn, it just doesn't have the horn, it was removed.
So, and
At
that
least
was the
that's what my
reason,
daughter thinks.
yeah, and that was the reason that we did it was you really can't calculate a probability at that point of a failure happening that would go beyond that.
Yeah,
So there was a lot of conversation about one, two, or three. And basically, when the PhD from MIT ran the probability analysis, you couldn't add enough decimals to 2 cells simultaneously failing inside of 4,300 in a pack. And that's why we did it, because
wow.
that's how we get to the term fail-safe, right? It's a fail-safe design. And that's it. And the beauty of it is architecture and really the system is if every electronic system fails, if every monitoring system fails, if every energy cutoff system and fire prevention, external fire prevention system fails, the pack can fail internally and you get no smoke, no gases, and no heat.
Wow. How do you do this? Or is it top secret? I mean, you must like have them contained within something super strong.
Yeah, so the pack's made out of 1/4 inch grade 50 metal. So the pack looks like an industrial pressure vessel.
So it's
It,
not each individual cell that it's the pack.
it's a combination of the pack design, the module design, and then the cell, the configuration around the cell.
Hmm.
Um, and there's three things that you have to solve for. One is you get 600 to 800 Celsius released instantaneously. So you have to absorb that energy very quickly. The second thing is you get particulate, right? You get little pieces of that cell that fly out and try to get to the next thing and
Like mini
transfer the energy.
shrapnel.
Yeah, like a
Uh-huh.
hand grenade, right?
Yep.
The third, which was the toughest for us to solve, was you get a sound wave. Because the pack is sealed, when that cell lets go, you get a concussive force. And depending on how the cell fails, that force can be directed at another cell. And what it does is it compresses the cell. And if you compress a cell, they can let go. We solved pretty quickly for the energy piece. We solved in a reasonable amount of time for the shrapnel because material science, right? You just had to give it something to go through to dissipate its energy. The sound piece was the toughest thing to solve for. And the way we did that was really we added a little bit of volume to the size of the pack, and then we added a spacing system. When that concussive force is released, it dissipates very quickly inside the pack, right? It can't be directed. It gets pushed into 10 or 15 different chimneys so that it can't consolidate, right? It just dissipates very quickly. And that was it, right? And once we got there on the sound piece, we could pass 10 out of 10 tests. And once we got to 10 out of 10, that's when we went into the final validation testing.
Okay. So I guess you must be doing UL 9540 and 9540A testing. Are you at that
Yeah.
point?
Yeah, we've tested to both of those standards. We've passed both of those. And what we did, Sean, is the thing about all of those current testing is it's really those tests measure what happens in a failure. They don't prevent you from having a failure.
That's the 9540A. Yeah.
So
So
it
it's
was,
like a fire test, and it's not really a test that you pass or fail. But then when you do, like from a installer's point of view, you get a battery that's 9540A, and then it'll tell you how to install it, and you can put the batteries closer than you otherwise would have to, like closer to each other. And residential, you could go closer than 3 feet per energy storage system and things like that. Just reminds me of another thing. Are you doing residential with your batteries?
so the majority of our systems are going to a single customer. So Sunbelt Rentals is using our
Oh,
50
great.
kilowatt hour pack and 150 kilowatt hour string. And we've configured them onto mobile, almost like a Moxion style unit. Um,
Really? Huh. So like Sunbelt Rentals is where I could go rent a Bobcat and an auger
yeah,
bit and make some post holes for my solar array and things like that. And it's like a generator, right? Is it?
yes. So the interesting thing about Sunbelt is they're one of the largest portable energy providers in the nation. So if there's a golf tournament or the Super Bowl or a catastrophic storm,
Yeah, we're actually had one here yesterday, and a lot of my friends are without power right now.
there you go.
I'll
Right.
tell them to go to Sunbolt, get them a Viridi.
That's it, right? So Sunbelt provides a lot of portable diesel generation to all these different applications. When you pair our 150 with a diesel generator, you create a hybrid system. And in that hybrid configuration, we can reduce diesel usage by 60 to 80%.
Oh, wow. Okay. Yeah, just like a standalone system. And then when you're doing that kind of stuff, what rules are you following? Because it's not really part of the building. What rules do you have to follow for that?
Yes, so what we've done is every time they have a deployment, we end up talking to the local AHJ, and we basically have a whole package that we pass through to them to show the testing, the design, and the pack architecture. And most of this gets approved by the local authorities, like an authority having jurisdiction would typically approve a large battery system, even if it's being used at a festival. If you're in, recently, we're looking at systems out at the San Francisco airport, and it was really the fire marshal for the airport in the local San Francisco that wanted to review the data.
So are you looking at the National Electrical Code and the International Fire Code and that kind of stuff?
Yeah, so look at the UL code is pretty standard, right? That would have jurisdiction over the fuses and the wiring and the electrical
Yeah.
design.
Yeah. So that's how the equipment is listed with the UL standards.
Yes.
And then the National Electrical Code will tell us to do that kind of stuff. But to me, it's just interesting that you're moving it around portable, which I think is really cool. I think we'll see a lot more of that. I was even thinking that one kind of neat thing about that is you could take your mobile energy storage system, like say if somebody had one at a construction site, and then take it home every night and charge it up or just bring it to the EV fast charger and top it off.
Yes. So here's two examples, right, of extreme uses that we did this year. So Pikes Peak, which is a racing event that happens every
Sure.
year.
Yep.
Okay, so we powered the Ford race team this year with 4 of our systems for fast charging of their race vehicles.
Oh, great. Yeah, they have like the electric cars going up to the top of this steep hill. I'm not sure where it is.
Yeah, it's in Colorado, right?
Colorado.
Like the race was originally founded by Henry Ford back in 1910 or something.
Uh-huh.
And Ford this year won their categories with this electric all-wheel drive van. It looked like
Oh,
like
awesome.
a cut between a minivan and a full-size van,
Wow, a van one. Okay.
but it was this monster electric vehicle, all-wheel drive, different battery systems. And the unique thing about our units is they're 150 kilowatt hours as a separate unit, but you can parallel together as many as you want. So you can literally put 10 of these trailer units on the ground, connect them together with a simple cable, and you can have 1.5 megawatt hours at 300 kW, 483 phase output.
Wow.
We were fast charging the vehicles off of our pack systems, and exactly what you just said, they were pulling the trailer that had the chargers on them down the mountain every night, plugging it into the Sunbelt depot
Uh-huh.
and charging the packs.
I'm wondering when you do that, when you fast charge the car, which is pretty much DC charging, is
Yep.
it going DC to DC or are you converting to AC?
So in this application, it was AC output into a AC to DC fast charger,
Okay, I get
but it
you.
was only because we really set all this up on a trailer to be mobile for them. They wanted
Yeah.
it right at the base of the mountain. So contrast that. So we're at the top of a mountain where it's probably 10 degrees and huge high elevation. We then sent pack systems through Sunbelt to the Burning Man Festival.
Hey, I've
And
been there before. Don't tell anybody though. Huh.
okay, we provided about 37 megawatt hours of energy to the Burning Man Festival this year
Wow. Okay.
out of these pack systems. And frankly, no, I don't know that I can advertise this because there's all kinds of NDAs and stuff. But essentially, when all that rain hit, the reason they never lost power was because our energy systems made the diesel generators 5 times more efficient. They didn't burn the diesel fuel they would have normally burned, so they didn't need to make diesel deliveries.
Oh, great. Okay. Yeah, it's been about 20 years since I've been there. So it was before the grid was modernized. But I remember one time I had a theme camp in Center Camp, and they did have their own electric grid there, which was cool for people that were in the Center Camp area.
Yeah, so I've never been there, but I know the units.
Or at least you can't tell anybody or you lose your CEO job.
Is that what happens? But it was a great use case,
Uh-huh.
and it just shows the flexibility of having renewable
Yeah.
power that you can use locally, right?
Yeah, I guess you can also compare that to like why a hybrid car is more efficient. Instead of taking a big megawatt diesel generator to charge a cell phone, you charge up your battery and then it's a lot more efficient to use it that way. Plus, you're running your generator at optimum, a certain RPM and a certain torque to charge the battery. And then you can turn off the generator and use the battery for a while.
Yeah. So clearly you've done this
Yeah, it's like with a PV system, maximum power point tracking. So you have this optimal combination of current and voltage. And so with a generator, you can have this optimal combination of like RPM and torque. So,
Yes. And the unique thing about our design is we have a very sophisticated IoT and control methodology on the units. So when you plug the generator into my pack system, I control the generator. So really what happens is the pack will discharge from full all the way down to about 8%. It'll signal the generator to fire up. The generator will fire up into your observation, run at full output for 4 to 5 hours, and then it'll shut off again for 30 to 40. In a worst case, in a very heavy usage, like 100% duty cycle, we save about 60% of the fuel. In an average duty cycle, we save almost 80%.
wow.
And carbon maintenance, everything else follows along with that.
Yeah. You can also even compare it to the early solar people. So you have some hippies living in the woods in the 80s or 90s, and they're using generators. And then they go out and get a couple of solar modules and a battery, and it works a lot more efficient that way.
Yes, this is the highly designed version of that model.
Mhm. Great, great. Let's see. One of the things that I was looking at, I was researching you a little bit on just before we talked this morning, and I looked at something where you were talking about, was it occupied spaces? I think it was, and that your technology can work in occupied spaces. And then we have different definitions too. So we have an occupiable space is a room or enclosed space designed for human occupancy. That means that people can be in it. And then we have a habitable space is a space in a building for living, sleeping, eating, or cooking, like bathrooms and even in bedrooms, of course, and things like that. So there's certain places where we can put an energy storage system in our house, but we can't put it in a habitable space, but we could put it in a certain closet or a hallway or something like that, or garage, things like that. But then another thing is, I reminded me too of you were talking about that your technology could go in an occupiable space. And so if you go right to the International Residential Code, section 328 or R328, we should say, energy storage systems. And then these are the rules that you follow for residential, for where you can put your batteries and stuff and things like that. And it says energy storage system shall comply with the provisions of this section. And then there's this exception right at the beginning. And it says an ESS listed and labeled in accordance with UL 9540 marked for use in residential dwelling units where installed in accordance with the manufacturer's instructions and NFPA 70, which is the National Electrical Code. So pretty much what this is saying is if you have an energy storage system that is marked for use in residential dwelling units, then you don't have to follow the residential code. And the thing is, there's no such thing as a UL 9540 energy storage system that is marked for use in residential dwelling units, because they're worried about the same thing that you're talking about, is having a thermal runaway. So perhaps the evolution of your system, if you make it so it's totally explosion proof, then perhaps people don't have to follow the residential code for that.
So we specifically tested with CSA to a
Yep.
residential standard.
Yeah, and so CSA is the Canadian Standards Association, and they are one of the labs that can do the UL tests.
Yeah. And in this instance, CSA and DNV partner,
Uh-huh.
and they're both kind of third party UL testing. And the reason they partnered was they really never, individually, they had never done a task like this, but between the two of them, they overlapped on their qualification. And they've never tested a pack this size to this standard, right?
Mm-hmm.
Because most of the, to your point in the beginning, right? Most packs are really small modules, right? They're 5 kilowatt hours or 10 kilowatt hours, or in the case of a Tesla, maybe 20 usable or 20 total, 15 usable. And if you test to that single unit, it's easier to pass because there's less energy.
Even Tesla has not, there's nobody that's been able to get it marked for use in residential dwelling units.
Yes.
Like 0 people. Yeah.
So what we did on the first installation, which happened here in New York State, was the New York Department of State issued us a building code variance that said, if you pass to this standard, and this standard is validated by the third party labs, CSA and DNV, we will allow you to install it in an occupied space, which in this case, it was a medical research building in downtown Buffalo. And the standard we created for this, Sean, went beyond 9540,
Okay.
9548. It
And
basically said on a pack level, you have to be able to force it into catastrophic failure, and you
yeah,
can't have any smoke, fire, or energy released from the pack.
yeah, and we can already, for the residential code, we can put it in an occupied space, just not a habitable space. I was saying we can put it in the hallways. And this is just for residential, which I'm talking about. So there's also commercial, and so they can put energy storage systems inside of a building, but that's interesting what you're saying.
Yeah, and my hope, and this is, we come back to these macro premises, right? So we look at this big issue about everybody focusing on electric vehicles and not on the rest of the economy. The second part of that kind of macro market view is look at our grid. If we look at our grid across the US and we look at it across 365 days, our grid operates at about 41% efficiency, right? 41% of total energy we generate and transmit and is available today based on the transmission system and the generation system. 41% of that actually gets sold through a meter, right? So about 41% of that total energy we end up purchasing as customers through our utility meters. And the reason is just time of day, renewables, coal and gas, and all this other stuff coming and going. It's really hard to match up customer usage with generation, transmission, delivery. If you put energy storage behind the meter, it's no longer hard to do that, because when it's behind the meter, whenever that individual meter is not running at capacity, the pack can take energy, right? It can optimize that connected system and take the energy that's not being consumed in a dryer or heat pump or air conditioning system. And then when you're using all those systems, the pack can take that peak and supply it. So, Sean, when we really succeed in distributed storage behind the meter, we can reasonably double the amount of energy we move through the existing system. And we don't have to build any more generation. We don't have to build any more transmission. We don't have to upgrade a transformer. We just optimize the system we've already purchased. And if we do that, the cost of energy has to come down. If we double the units going through the existing system, economics would tell us twice as many units, same asset, it's going to get cheaper. And it's 100% resilient and manages spikes and voltage drops. Like, the reason our fossil system is so good is because it's based on storage. We just never looked at that concept for our electrical system.
Yep. One of the things that I'm thinking of maybe for a neat future for your type of mobile energy storage systems is, let's say there's a power outage and the utility comes out and they bring a whole bunch of trucks and they're fixing power lines and using their chainsaws to get the tree out of the way and all that kind of stuff. They could bring 10 or 100 of your energy storage systems and get the grid going again. And so you would need the technology to do microgrids and things like that and lots of coordination. So I think that it might take some time for technology to get there. Have you had any talks about doing stuff like that, or including the energy storage system in a microgrid? Even when it's sitting there at the Sunbelt rentals waiting to get rented out, you could help support the grid. So not only behind the meter, but you could be exporting from behind the meter, especially at key important times, to help the grid. And sometimes those kilowatt hours are worth a lot when you're exporting them to the grid.
And Sean, the conversation today with you and the conversations we're starting to have with other groups is really to highlight the optionality that we can bring into the system by having safe storage. And we literally finished the testing 20 months ago. The month we finished the testing, Sunbelt came in and said, okay, how much can you make next year? I want to take it all. Like, they bought out next year. So we are just starting to have conversations about other uses. And Alex obviously thinks very highly of you. And as I went through what you've done in your career, it's incredible how long you've been in the energy space.
Thanks.
We can fix this, right? I think the point of all this is we can be more cost effective, we can deliver more resilient energy, and we can do it in a more balanced and renewable way. But we have to solve that. Right? We have to solve for those three. Like, the only way people are going to convert is if it's less expensive, it's a better product, and then everything else follows. And that's what we're focusing on, right? How do we deliver a better product? And if we deliver a better product, then the politics don't matter anymore, right? Nobody's going to argue about something less expensive that performs better. And I think that's where, as an industry, we have to challenge ourselves to go. Because if we're going to get past all of the noise, The only way to do it is get rid of the argument. It's just better. What's your issue?
Yeah, you know what else? I just thought of something funny, and I'm not sure if it's very practical. Is let's say that somebody buys an electric vehicle that only can go 100 miles because they want to spend all that extra money on the batteries. So they could tow along one of your portable energy storage systems for those long trips that don't happen very often. And so it's the cure for range anxiety. But
I mean, listen, I'll tell you one of the projects we're working on right now, which I'm hoping to have done and through concept before the end of the year, is building what I would call fully renewable fueling stations for electric vehicles. Everybody says, look, our country's so big and we got all these remote areas. Well, most of those remote areas have a hell of a lot of sunshine, and we're not space constrained for panels. It would be simple to put up 10 or 12 acres of solar panels on any of our highways that run across this beautiful country, connected with battery storage and EV charging, and have basically remote or operated stations that are completely off grid.
yeah, great. I'm wondering too, with the portable technology that you have, is there anything ways that makes it easier as far as codes and standards go because you're not part of the building?
Yeah, so one of the things we're talking to New York City about right now, and we're going through a process with the fire department and a couple of the other agencies, but within the code today, if you have a less than 250 kilowatt hours and it's connected to an EV charger, you can use that system in the city if it's portable. And we have that configuration, right? We have a 150 kilowatt hour system with an EV charger on the front of it. Yeah. And look, it makes all the sense in the world, right? If it's on a trailer and you can move it around, it's no different than a car. The difference with ours is that you can put it next to the building and have assurance that it's never going to cause an issue for those deployed assets.
And do they tell you like how far away from the building you have to park, or is there any about that?
Sean, everybody's working through this right now. So I think we're developing the rules, and we're starting at a point where we're saying, look, the technology is fail safe, and that should be part of any code design, right? Once you do that, then you're really just solving for the issues that we solve for every day in our economy, which is, okay, where do you park it? What's the best place to put it? Do we want access to it? All those other, what I would call infrastructure planning issues.
So are all of the energy storage systems that you're working with right now, are they all portable?
No, so we have place systems. That is it. There's a medical campus in downtown Buffalo that has a 600 kilowatt hour system installed in the building. To my knowledge, it's the largest indoor battery system that was done by a permit in New York State, if not most of the country. We have a number of projects right now that are getting installed in buildings.
So speaking of Buffalo, you're sitting in Buffalo right now. Tell me a little bit about the building that you're in. Is that your headquarters?
No, this is a building that's I'm tied to through another business activity, but our headquarters in Buffalo it's in a zip code that's 14215. The facility was built 100 years ago by General Motors. It was the first GM plant outside of the state of Michigan as they were expanding.
Great.
And expanding into Buffalo at the turn of the 18th century, 19th century, because Buffalo was like the second or third fastest growing city in the nation. Now that neighborhood has gone from one of the fastest expanding neighborhoods at the turn of the century to challenge zip code in New York State. So 14215 has the highest unemployment rates, the highest number of single owner home ownership, the highest rates of public assistance, and some of the highest crime rates, actually the highest crime rates in the city and almost in the state. We were very intentional about locating there. And the whole concept of locating there was find a way to embrace that local neighborhood, bring them into this technology, and take individuals that really don't have opportunity in that neighborhood and give them a place that they can walk to and work.
Great. That's great. I do a lot of classes for unemployed people and things like that too. I was just noticing too on the Viridi website, I just click on about, and I can see you here at the top, founder and CEO, and it says the first half of your career that you were focused on removing and remediating the remnants of the Industrial Revolution, that darn Industrial Revolution. So what are we in now? Like we're post-Industrial Revolution. What would you call the time that we are in, which is pretty amazing. I was just thinking the other day how amazing it is. I think they say about, at least I asked Chat GPT, it was like, when was the date, if you had to give one, when we switched from cars to horses? And it came up with like 1913. And it's just pretty amazing to me. Like you look at an old movie and you see like 250 BC or something like that. And then you see something in 1850 or even 1900, and it looks a lot the same. They're riding horses, and then all of a sudden we have rockets and we're taking jet airplanes, and it's amazing how fast things have changed in the last, I don't know, like 120 years, something like that. So where would you say that we are right now?
I think, Sean, to your point, right? And when we talk about the most visible societal change is when you see horses and carriages and then you see cars. But what happened in that period that isn't visible is we went from being basically captive to where energy was, right? So we located next to rivers. We used different mechanisms to tap into natural movements to create energy. And
Yep.
once fossil was developed, now we could put energy where the use was, or the application, or the need. What happened was energy was now portable. And when energy became portable, we expanded in a way that nobody ever imagined. The next 50 to 100 years is going to take that expansion that happened 150 years ago and make it look like a rounding error, because we're going back to embracing natural sources of energy, but we have the technology now to optimize it and make it portable, right? So back then we had daylight factories because when the sun came up, we would work. And when the sun went down, we wouldn't. We don't need to rely on when the sun's out now to harness that energy. Same thing with our rivers and streams, right? We would put a paddle wheel in a river and locate our mill next to that paddle wheel because it was a captive source of energy.
Yeah, they didn't have good high voltage transmission back then.
They didn't, right? So I think this is the most, I think we all say this, right? Hopefully, but this is an incredibly exciting time to be alive. I think as we push ourselves from an engineering standpoint to be smarter and faster and better, everybody will come along in this conversation. And look, I think there has never been an argument against being more efficient, right? And sustainability is just being more efficient. Like we rely on an energy source now where 80% of that potential energy goes out the end of a pipe. That's not efficient, right?
Yeah.
As we transition to electricity, we can get up to 90, 93% of that energy in output. We just have to show the economy as a macro unit that it's more cost effective, it's more efficient, and it's more sustainable, right? And we can do that, Sean. Like this is math. We're pretty good at math.
Great, great. Tell me a little bit more about yourself. Where did you start off and where are you going?
Yeah, I started in the environmental remediation business, and most of our clients were big corporate industrials. So companies like Honeywell, Occidental Petroleum, and Dow Chemical. I mean, any of the industrial powerhouses that really created either chemicals or the industrial processes that power the nation. And most of those organizations had 100 years of industrial activity, and they had sites that no longer had a productive output or a productive purpose. But we would go into these towns and cities that had these huge factory footprints, and we would remove the factories and clean up the soil and put a fence up. And you felt like an undertaker, right? Because as long as the building was there, the community had hope. And
So,
even though the building was a mess, they still had hope, right? But when you came in and got rid of the building and you cleaned up the site, okay, somebody said, well, maybe we'll put up a soccer field, right? And 1,000 jobs went away.
yeah, I know they're doing the Inflation Reduction Act. It has some benefits for, say, putting renewable energy projects where an old coal mine is to keep the jobs
Yeah.
where the old coal mine is. And so people, they're doing that kind of stuff, which is kind of neat.
And Sean, like when we talk about being more efficient and more sustainable, right? When you look at a former industrial site, all the roads are already in place, all the gas lines, typically all the rail lines. You've got water and sewer and electrical infrastructure. When you repurpose one of those sites, you basically leverage and add units of billing to an existing infrastructure. But when we go 20 miles away and we create it in the middle of a farm field, we force the community to bring all those infrastructure assets, spend more money, extend those assets, put in new power, new gas, new roads, new lights, new schools, but we don't really increase the tax base, right? If we focus on these former industrial sites, we create density, we put jobs where people are. So we reduce the need for transportation and these huge, what I would call public road systems. And we leverage assets that we've purchased and spent money on over the last 100 years. So the point is sustainability, right? If we do it at every point, this works. And look, there are times when you have to expand your footprint, right? You run out of real estate. But in most of our industrial centers today, there are massive swaths of real estate that have infrastructure completely developed, yet they're way underutilized from an acreage standpoint.
Tell me more about the building that you're sitting in right now.
It's an old powerhouse. I'm going to give you an interesting story, and I don't, you can cut me off if it gets long. But at the turn of the century, right after World War I, the US and its European allies realized that almost all chemical manufacturing technology, capacity, and infrastructure was located in Germany. Germany had essentially a monopoly on chemical manufacturing. And not just the manufacturing, but the knowledge base, the institutional knowledge, and the designs. There was a family called the Shelkoffs, which were German based, that immigrated to the US. Shelkoffs built what was called Shelkoff Chemical on this site in like 1908. And then Shelkoff, about 10 years later, merged with a company called the Aniline Chemical Company, which was based in New Jersey, to form Allied Chemical. And, Allied at the time, in 1965, Allied was the largest industrial corporation in the world.
Wow.
But Sean, when it was formed in like 1918, the reason it was called Allied Chemical was because the US and the European government got together and said, we need to bring our largest chemical companies together. And the Allied, need to repatriate chemical technology so we can defend ourselves. It was called Allied Chemical because it was the Allies, like the Allies created the entity. And it, the largest plant in that system was here in Buffalo at the site I'm sitting on now.
So if that didn't happen, we might be all living under some kind of dictatorship right now.
It might have been a different world. Yeah.
That's kind of neat. And so you're sitting in there in that building right now. I know another famous guy that did some work up there at Niagara is Nikola Tesla.
Yeah, I mean, look at Tesla, Westinghouse, right? They all came from this region. And yeah, so this was one of the first industrial facilities that received hydropower from the plant that Tesla and Westinghouse built.
Wow, that's an interesting plant too. It's like we think of electricity as being single phase or three phase, and somehow they had two phase when you look it up, that first Niagara Falls AC power plant. And the big benefit of AC, of course, is you can boost and drop the voltage with transformers and go long distances. But now we're seeing high voltage direct current too, where people can go long distance by boosting up and down direct current. And so that's kind of neat too.
Yeah, so it turns out Edison was probably right. He just didn't have the technology to prove it at the time.
Yeah, to figure out how to boost it and drop it like that. Didn't have those semiconductors. And so the reason that it works better with direct current is because you could make full use of the conductor with alternating current. You have this thing called skin effect, and the current likes to travel around the outer part of the wire. That's one of the problems with alternating current.
I don't know if you've seen what National Grid's doing in the UK, but they are embarking on the largest infrastructure development project I think any utility's done in probably 100 years. And they're running DC cable under all of the waterways around the UK to pull wind power out of the Nordic. It's about an $8 billion infrastructure investment. And they're doing just what you're talking about, right? They're transmitting by DC, and then they're coming up into switching stations to go from DC to AC and go back into the existing transmission system.
So they're bringing it up the big rivers and like the Thames and all that?
Well, like if you go on their website in the UK, they actually have it mapped out. And I'm not familiar with all the seas and the waterways that surround England.
But the one that goes up into London, that THAMES, I guess how you spell it.
It is really cool to look at the map because you see the lines kind of going everywhere. And they're doing direct burial in the sea.
Wow. Okay. That'd be a good way to go fishing too, if they could figure out how to short it out when the school is coming by.
Float a whole sea of fish. Right?
Sorry, fish. Just kidding. I hope I didn't offend anybody, but I'm all for the fish. All right. Is there anything else that you wanted to talk about? And then you can also let us know about where people can find you and your company.
Yeah, the website is veridiparente.com. And I apologize for both those words being Latin. The good news is you spell them phonetically. So it's a pretty clean spelling.
What does parente mean?
It means parent.
Okay, so green parent. So VIRIDIPARENTE.
Yes.
And now we're all speaking Latin.
Yes.
Viridi Parenti. Great.
And look, Sean, I really appreciate you making time to do this. Happy to
Oh,
follow
it's been
anything
fun.
you need. And I would like to try and get more information on the training because, like I said, we are new into the market and we're really trying to get our techs up to speed on all of the kind of national and regional training requirements that are recognized in the industry.
Okay, great. Yeah, I do lots of NABCEP training, and that stands for NABCEP, North American Board of Certified Energy Practitioners. And I prepare people for NABCEP exams. I give them continuing education classes and things like that. In fact, I am going to be at the NABCEP Continuing Education Conference in Raleigh, North Carolina, coming up, and not too long from now. I'm going to teach the PV Associate class, and that class is going to be in March, and it's going to be March 18th to the 21st. And the NABCEP conference is also a lot of fun. If people wanted to find me, they can go to Solar, SEAN, that's solarshawn.com, and you can find links to all my classes. I have a lot of classes that are on heat spring, and I'm also traveling a lot, teaching different classes for different people. I teach everything from returning citizens all the way to engineers, and perhaps even some engineers that are returning citizens. I have to figure out if that's the case, but that would be a lot of fun. And I'm doing a lot of stuff in Boston coming up recently, coming up in the near future. I'm going to be there next week and going to be there a couple other times. So for some reason, it's Boston season right now. I just was there a couple of weeks ago too. It was a lot of fun. And so thanks so much, Jon Williams of Viridi Energy, for joining the podcast. And thanks everybody for listening to Shawn White's Solar and Energy Storage Podcast.